everyone, so in this video we're going to be going over Dalton atomic models. Now there's three key ways that you can actually represent elements. Dalton atomic models are the simplistic way because with our Dalton models we're representing our elements as circles, and the relative size of the circles is reflective on the relative size of our element. There's Bohr-Rutherford models, which has the most detail about the atom in the sense that it has the total number of protons, the total number of electron shells, the total number of electrons, and the total number of valence electrons. And then we have Lewis dot diagrams that show us the chemical symbol and the number of valence electrons. Now, Dalton models are particularly useful for when we are doing chemical equations. And we would see mostly Dalton atomic models when we're drawing out chemical equations. And this is particularly useful when we're doing showing chemical equations in the concept of the law of conservation of mass. And when we're talking about the law of conservation of mass, this is where we have our total mass of our reactants. So the total mass at the beginning of the reaction equals the total mass at the end of the reaction, which also means that the total number of elements that we have at the beginning of the reaction equals the total number of elements that we have at the end of the reaction. So we're going to go into a little bit of detail and show an example of our atomic models. So as I said, Dalton models, we normally represent them as circles with the element symbol on the inside. So if I was showing hydrogen, it'd be a circle with H. So that would be hydrogen. Let's say I was showing the molecule oxygen. So this would just be hydrogen by itself. If I was showing the molecule oxygen, well, if I'm looking at this molecule right here, remember I have my little 2 here, which is my subscript, which means that I have 2 oxygen atoms in this molecule. So to show it, it would be 2 circles of oxygen touching with the element symbol on the inside. You can use color codes here, but it's probably much easier just to write the element symbols. So also the sizes of our circles are reflective of the relative size of our atom. So let's say I was trying to draw water. So if I'm drawing water, my molecular formula for water is H2O, meaning in the sense that I have 2 hydrogens for every 1 oxygen. So I would have 1 large circle for oxygen and 2 smaller circles for hydrogen. And the reason why hydrogen is smaller than oxygen is because if I look on the periodic table, I can look at my atomic mass. And if I'm looking at my atomic mass, so recap all elements on the periodic table, have a box where I would have the chemical symbol. So it's the 1 or 2 letter symbol to represent the element. I have my atomic number, which is the whole number on the top that tells us the number of protons, and I have my atomic mass. So if I'm looking at hydrogen, right, my atomic number is the whole number on the top. So in this case, hydrogen is 1, so that means I have 1 proton. And if I'm looking at the number at the bottom underneath the chemical symbol, this is my atomic mass, and that tells me the relative mass of the atom. And the saying goes, the bigger the atomic mass, the bigger the atom. So if we're looking at hydrogen, the atomic mass is 1.01. For oxygen, it's 16. So oxygen is 16 times bigger than hydrogen, so that's why my circle for oxygen is a little bit bigger. Let's say I was drawing the Dalton model for ammonium, so ammonia, NH3. So if I'm looking at this, I would have 1 nitrogen because I can see that there's no subscript here. So I have 1 circle for nitrogen, And hydrogen, I see the subscript 3, so that means I have 3 hydrogen atoms, and they are all touching together because in my molecule I have 1 nitrogen and 3 hydrogens. So this is a typical way that we would draw our Dalton models. If I'm just drawing the particular atom, it would be by itself. But most of the time when we're drawing our molecules, we would have each circle representing my different element, the subscripts telling us how many of that particular atom is in that element. So if I'm looking at oxygen, molecular oxygen is made up of 2 oxygen atoms, so the 2 oxygens are bound together. Molecular water is made up of 2 hydrogen atoms and 1 oxygen atom combined together. And if I'm looking at my third example of ammonia, I have 1 nitrogen atom and 3 hydrogen atoms. Now, another typical way to draw Dalton models is to draw out our chemical reaction. So again, if I'm looking at my chemical reaction, my subscript is only really talking about the element directly to the left of it. So this 4 means that in CH4, I have 4 hydrogens. Now, my coefficients, and my coefficients are the big numbers in front of my molecule. That tells me how many times I'm drawing that molecule. So if I'm looking at if I'm looking at oxygen, I have a 2 in front of the oxygen, meaning I am drawing 2 oxygen molecules. So if we get drawing with our reactants, I see in methane, I have 1 carbon. Let's draw this a little bit nicer. I have 1 circle for carbon, and I have 4 circles for hydrogen, and my hydrogens are smaller than my carbons because carbon has a bigger atomic mass than hydrogen. So I have my 1 molecule of CH4. Now I'm drawing my 2 oxygens. So I have 1 molecule of oxygen gas, and I have 2 molecules of oxygen gas. And I can see my coefficient is telling me how many times I am drawing the molecule. So the molecules are not touching together because in 1 molecule of oxygen gas, I have 2 oxygen atoms chemically combined. Because I need 2 molecules, I'm redrawing that first picture 1 more time. So I have my reactants, and now I'm going to draw my products. So if I'm looking at my products, I have CO2, so that means I have 1 carbon and 2 oxygens. And I have 2 water molecules. So that means in each water molecule, I have 1 oxygen and 2 hydrogens. Again, the oxygen is bigger than the hydrogen because it has the mass of oxygen is much bigger than hydrogen. And I can see the size of my circles for carbon and oxygen are practically the same size because their masses are relatively similar. So again, this is how we draw our Dalton models. I hope this helped, and have a great day.